Okay, thank you for being here. This is, I feel a little frazzled because I had to get the link first and I was confused by that. So I apologize for the late start. I'm Sandra. I teach at Rochester Catholic Schools. I was born and raised in Germany. So all my education so far has been in Germany. I grew up there. I went to school there. I was educated there. I moved to I have a German degree for teaching math and history. And I recently, 2022, 2023, graduated from the MNCodes cohort, which is why I'm here, because Liz and Ashley taught me that I should present on this as a math teacher who also does a little bit of computer science on the side, but still doesn't feel like anywhere close to an expert. Let's put it this way. So for this purpose, I'll just want to dive in about fostering computational thinking in the 6th to 12th math classroom. I assume that everyone at least has like a basic algebra level, algebra 2 level of math that's in this room, because that's more or less what this covers. Algebra 1, algebra 2 is what I'm going into. So please let me know if you're not comfortable with this level. Let's dive right in. This is straight from one of those textbooks, and although this textbook is 17 years old, it's still used by my colleague in our school. Error analysis. Student solved the equation without showing all the work. Student solution is incorrect. What error did the student make? Question would then be, have you ever assigned such a problem? And what is the benefit to assigning such a problem versus just solving this? Or solve this problem is one thing, like without, oh, this isn't just solve this two-step equation. That's one question. Everyone could do this. The second, hopefully, or getting there. And then the question is, why is the error analysis such a bigger question? Because it's a number 28 and not a problem 8 in the textbook. Usually means a little more complex. So what's the benefit of doing something like this? And there is evidence that those error analysis tasks lead to a higher retention of knowledge. Questions is, how does this link to computer science? Computer science and computational thinking, which computational thinking is another big word that this session is about. As you can see with the graphic here, computational thinking is just a part of computer science. And both of those bubbles, they overlap, hello Venn diagram, but they're all part of the bigger computing bubble. This link is from Digital Promise. And there's some statement from the same website, Digital Promise, that where computer science as a subject is not yet offered, integrating computational thinking, the other bubble, can empower educators and students to better understand and participate in the computational world. And also that there are benefits if you do both. If you already have a computer science class, students can still benefit from computational thinking tasks outside of that designated computer science class. So what is computing? What is computational thinking? That's, for some people, that's kind of the same, thinking like a computer. Computer does calculations. So computation or computing is a skill. We learn that mostly in elementary school, like all your addition, subtraction, multiplication facts, and the fluency of them. Just like knowing, oh yeah, I know what 6 times 7 is. That is computing. One step ahead, as I would like to say, but that might involve a little bias, is computational thinking as the thought process that is involved if you want to express solutions as computational steps or algorithms that can be carried out by a computer. I just came from the session with Andrea, and Andrea said something like, ask your favorite machine learning, language machine learning, ChatGPT or whatever, what computer science is, and I'm pretty sure computational thinking would get a similar idea of what that could be. So all of those thought processes that are involved in computational thinking are transferable to any other curriculum area, but the soon to be, or not so soon to be implemented 2022 math standards, they integrate computer science in those two, or computer science skills to them. Computer science context is what they called. So field of study that focuses on learning how to think computationally. So that's the computational thinking part. And then we also have adapting and creating new technology part. Many connections with math. I guess that's why a lot of secondary math teachers also at one point turn into computer science teachers, or are asked to teach computer science as well. So, and as the previous statement said, deepening students' understanding in math. So there's a link between the understanding of one subject to the other, providing more students with access to computer science. I've learned that that's actually one of the biggest pulls why they have the integrated computer science standards, because then educators have to make sure that all students are exposed to them. That's from Sarah Carter, who is also of the Minnesota Department of Education, from a talk that I heard, I think last year at the summit. So that's the whole idea of integrating. If it's part of the academic standards, every student needs to be a part of it. So, and any number sign in the new standards represents computer science context, number sign, pound sign, however you want to call that. So sometimes the pound sign is more technology use than the actual thinking computationally. So create this visualization about a data set in the now biggest trend data analysis, has the pound sign, also has the modeling sign. So that's how this standard is written. You could think maybe Microsoft Excel or a spreadsheet of your favorite provider. So fun to know that those data collection displays also one of the skills strands in computer science from the teachers associations. I can't speak. So there's a lot of things in in the math integrated standards that are more technology. But then we also have, what's going on here? Oh, we also have this pattern and relationships, which if you look at the benchmark closely, this is like order of operation. Evaluate algebraic expressions, including expressions containing rational numbers, by applying computational hierarchy of operations at specified values of the variable. And this also comes with a pound sign. And yes, I guess a lesson in Google Sheets would also do the trick to explain why we need parentheses sometimes to emphasize things and things like that. But this is a little less obvious a pure text skill. So the question is, how does the computational thinking skill come in this? And again, if you look at those little numbers here, just as a side note, MP7, in this case means look for and make use of structure. The skill before was use appropriate tools and attend to precision. So what does this thinking computationally mean? This is one of my most favorite pictures ever. Like the computational thinkers. What are computational thinkers? What is a person that thinks computationally? We have concepts on one side, we have approaches on the other side. And most important thing, everyone is capable of computational thinking. You might have already integrated in your classroom. What is going on here? When we think about our order of operation skills from the slide before, where do you see order of operation skills in this poster? And if you're watching this after the summit, that's one thing. it's a little weird for me, honestly, to interact when there's one audience member, but thank you for being here. Yeah. And it's also weird because I'll take you to the spot. It's just like, how do you see this order of operation skills? And I can give you the answer, but I will do that in a bit, but some interaction at this point was planned. Again, I didn't know what to expect, but if you want to say something, write something in the chat, please feel welcome to do so. I'll get a little bit more personal and a little bit later. Computational thinkers. Order of operations, algorithms, I guess. Definitely, there are steps and rules, and if the order of operations aren't rules, then that's one thing. Also maybe tinkering, changing things to see what happens as an approach. Okay, what if we didn't have those parentheses there? What if we would do everything from left to right without any rules? And then seeing, okay, we need to break those problems down into parts, do it in that specific order because we have to agree on something. So just this computational thinking approach in this case is like really, okay, let's consider the order of operations. Why do we need that? What is the reason for them? In order to then agree on a set of rules or make it obvious why this set of rules has been agreed upon. Because we need a hierarchy in order for everyone to be on the same page. And for the whole poster, I teach middle school advanced math, so that's mostly algebra standards, algebra 1, algebra 2, to 7th and 8th graders. I get a lot of algebra vibes from all of this, from all of those approaches or concepts that are in this poster, because what else is algebra than patterns, for example, or decomposition, or all of those things above, algorithms? What else? What's a better description of algebra? Okay. So if you think again of this poster, and also again of the order of operations, we have the concepts of decomposition, we have the concepts of tinkering, we have the concepts of algorithms that you can all cover and ask students to be computational thinkers by not only tell them, oh yeah, this is PEMDAS, this is GEMS, but have them rather explore or decompose or tinker around with a big what if. If we look in the couple of slides back where it was about the visualization about a data set, organizing, presenting the data, that's for example, the concept of evaluation and others, whatever else you want to put there. And the very first example that I started the slideshow with, the error analysis, call it debugging, because something isn't working, we have to figure out why. And whether students have already experienced that in computer science, in a separate computer science class or not, it might make it a little bit more approachable for students to just value the, hey, this is when you do computer science, when you do programming, you have to do that all the time. Something isn't working, we have to figure out what it is. So a debugging approach for all those error analysis problems. So all of this together, chances are you have taught computational thinking skills without actually knowing it. Next step would then be to be intentional about it. For this, and this is a semantic wave I've heard just very recently, about being intentional regarding those instructional strategies. Semantic wave, not sure if you've heard about it. So you have oh, that's an algorithm, you always have to do this. Okay, what is a precise sequence? What is a step? So then you go back, yeah, that's like instructions recipes, like a how-to. So you could go back with activity to use instructions or recipe. I like to introduce my students to combining like terms with these mad sketch, where someone puts a like very weird order into a fast food place that is all over the place, and they have to like kind of, it would be more efficient if that approach. So that's could be an activity using instructions or recipes. But the important thing is then we put it back together and then make the distinction between the recipe or the fast food order back to these abstract and complex meanings. It's not a wave if it's not completed, if you don't go up. If you keep it at this level, it might be easier for the student to grasp, but they're not getting back up to abstract and complex meanings. By the way, I'll try to keep an eye on the chat, so if you have anything to say, please feel free to do so. And again, variables. What is a variable? A symbol. Students are overwhelmed when you first put letters into math that has so far only been numbers. It's just like, what's going on here? And then, okay, this X can be for anything. It can be a red box, it can be a square, it can be a heart. 5 hearts plus 4 hearts, what does that make? And then just go all the way back up to, this case, variables, algorithms. And this explanation that I copied down here, explain variable using boxes. The educator might explain variable using boxes. That's actually what I do with my middle schoolers when they first get to use those boxes. Again, it's not only about boxes. They must help learners link it back to the technical and abstract meaning, so they can serve back up. And this whole explanation is actually from the computer science definition of a variable, but the same thing also applies to algebra as a variable, just to make things a little bit more digestible as a potential best practice. When it comes to my own classroom, and how I foster computational thinking there, I just wanted to share some of those ideas first, and then the physical requirements that I installed in my classroom. And I think I actually read those books in order as a mandatory or not so mandatory professional development reading. First, I read Ditch That Textbook. I came here, I started my position that I still have. I was hired at a very short notice, and I had taught math in Germany before, but I had subbed before, and I noticed that there was a difference in subbing an American classroom versus teaching my own classroom back in Germany. So I had to kind of fill the gap with what to expect, what am I doing, what's going on. So that's kind of the idea of, okay, I have that textbook, that's my lifeline for this first year or two. And then I noticed this textbook is not covering everything that I want my students to know, especially in the some deeper thinking. So I ditched that textbook and aligned my curriculum more or less to standards and made it a better flow. The textbook had the equations units split up into 1-step, 2-step equations, then the whole thing with fractions and decimals in it, and then I think another unit in between, and then they went back to multi-step equations with both on their own and then with fractions and decimals. I was like, oh, that's not a good flow. So that was more about anything about the flow of the class to ditch that class book first. Then when Twitter still was Twitter and it had a great professional development community, I found Open Middle Math. I was a volunteer there for a while as well. You'll see Open Middle Math problems in a bit. So if you're not experienced, if you have no experience with them, that's coming up to what that means. And the last book that I read, and I also was in Duluth a year ago to hear him speak at the math teacher conference up there, building thinking classrooms. So I took like a little bit of everything, not to the extreme, not doing it all the time, but with all of those approaches, I learned that it helped me to focus more on the why am I doing this versus the how am I doing it. So that has shifted my teaching approach from book gives the instructions, and then gets gradually harder to focus a little bit more on the why. Again, that's what rocks my boat. You can modify whatever rocks your boat. Students are more likely to be engaged if they actively think and talk math. I guess that's not a new thing either, but also part of what I noticed in the beginning. So this is my classroom at the beginning of the year with the big boxes in there at this point. So I do have the inspiration from building thinking classrooms that I do have whiteboards everywhere in the room. Don't mind this big box. I got my smartboard replaced. And then I do have random groups that looks different now too. And I usually assign those random groups when the students come in at the beginning of class, and you just hand out a card, all the 2s, all the 6s, all the 3s, all the 4s, all the kings, all the queens, all the jesters. They all go and meet in that group. That seemed to be the best thing for me to do. So if what does it feel like? And at this point, I would really like to invite you to tackle that problem. What numbers go in the blanks to make the equation 2? And this is a problem from the Open Middle website. The link works, so if you have, I think later they'll send it the material, so you could look at it there, be let right there. If you click on the link to the website, it will also have some links, some hints and a solution as well. So try this out. And then how do you solve this? How do you get to a solution? And is there only one? Are there multiple solutions? It's kind of so most of my students, I usually introduce factoring with a box method. Most of my students would kind of see in the very beginning, okay, I'll get this. If I want to get the 4x cubed, I need to have a 2 over here as well as the leading coefficient. And then they would maybe make the box and figure out from those two middle terms what number goes in here. If I remember correctly, that's a 6. And then again, computational thinking concepts, approaches, just as an idea, to remember. You could just tinker around as the approach, just see, okay, change things to see what happens. If you didn't see, oh, there's a 2 right away, maybe start making this a 1 at first. You could still tinker around, see what happens if that's a 1, and then you notice, oh, that doesn't work out. I need to use the 2 there first. A lot of it is persevering. My classroom, it also would be the approach of collaboration, because I assign them in a random group of mostly 3 people that are working together to solve that problem. Decomposition as a concept, I need to break this down. If I look at the box, I need to look at my individual terms to see how things work. The patterns of maybe the box method, like spotting using similarities, maybe they have factored something before that starts with 4x cubed, so they know it can either split up in a 1 and a 4 or a 2 and a 2, so there's only those 2 options, and since that already is a 2, well, then the other thing also, the other leading coefficients also has to be a 2. And evaluation, So lots of things that are going on. And in the end, such a problem like that can often take them 5, maybe up to 15 minutes to solve. So yeah, that's a lot of concepts that I met in this one. This, also from openmiddle.com, is one of my favorite problems ever to solve, to give to my students. In the middle of the unit on inequalities, or towards the end of the unit of inequalities, I often put modified questions of this on the unit test as well, if we've done similar questions on the unit before. Because this question alone can easily replace a whole worksheet of solve this inequality, I think. So one of those things is you want the x to be less than -1/2. So the sign has to flip. And if students, again, you will most likely have all kind of students. Some of them will just like get it right away. Although not a lot of my students did, honestly. Some of them will struggle to get anything going. I usually, the first hint that I give them is, if you want this to be the solution, what's the step before? To work backwards, to decompose, make this problem a little less, a little smaller, so to speak. So work backwards. Start with x is less than 1/2. So what could the step before look like? And then go all the way back. It's, again, more thinking backwards, more thinking, okay, making judgments, a little higher level of learning, because it's a different way of thinking, as to just solve a set of inequalities with variables on both sides. Again, I do not claim to have invented the wheel. It's just what works in my classroom. Is everyone able to contribute something? That's another thing, because in my groups of usually 3, when I send them off to the whiteboards to solve a problem like that, I only give them 1 marker per group. So they have to figure out what to do, how to use it. Can everyone say something? Will some people like just zone out and not learn anything? Usually the beginning might be hard for some, but then it's just the keep on going, just like, oh, we are so close. We got -1/3, or we got 1/2, and it's not switch the sign, but the numbers are right. So all of those ideas usually keep them more motivated to get going, because they see the efforts leading to something. Okay. If you want more than this, because you can do those problems even if you do not feel comfortable with any level of technology. This is something that everyone could incorporate in their lessons. But again, if you want more than that, you could, for example, look into csnmath.org, which is an absolute great website, from part of it done by Ashley, who's also one of the code savvy educators. So it requires some knowledge of block-based coding in Scratch. And again, there's some PD that MNCodes offers on Scratch. And that's Scratch MIT. So even if you're not going into depth with the actual coding or programming, you can kind of focus on writing pseudocode. So what has to happen between the input and the output? You don't actually have to go into Scratch. You can just have students realize, okay, this is how that would work. I had one of those very rare years where I was done with the curriculum, or the learning goals, at 2 weeks before the end of instruction. So this is actually what one of my students created. And usually click on this. And it will, oh, I need to click a space. I need to look into my instructions again. So space to reset, type in 2 size and you tell your third, make sure that C is bigger than A and B. So if I type on this one, why does it not run? Why are we not running today? Ah, there we go. I have to click on Scratch first. What's A? If you don't know, write question mark. So let A be 4. Enter. What is B? B is 3. And then what's C if you don't know that? That's my unknown for the time being. It's calculated. When you type it in as a question mark, it's calculated. And if you look into the code, the actual code, that's when this spread is clicked, ask the question, wait for the answer. And this is the math part here. So they need to have the code for the Pythagorean theorem, like rewrite formulas if they want to make the variable accordingly. So that's, again, student-created product after just a short intro into Scratch. And they also have website on this, also resources on the csandmath.org website. Just the idea, okay, if I want to give the computer only one variable, then I need to solve for the variable first, because otherwise the computer can't digest the information quick enough. And another math skill here, computational thinking, actually with a little bit more physical computing itself, programming itself. If you want to look into this data visualization, that's my trigger word for today. Also from the new math standards, there's a 45-minute lesson there, which is on code.org, Code Studio, where students, they are also pretty good at giving instructions. If you click the link on this one, it's all in the app lab. There's this course alignment. The main activity is making bar charts and histograms. And again, there's the data visualization activity guide for this, and the actual data thing, the useful and non-useful classifying data. A chart that is useful. So they're making those histograms. For the link, where that is right now. Yep. So they have a video before, and then that's the digital form for it. And lots of other things. Okay. We can actually tinker around, and besides your favorite spreadsheet, can make the bar charts in a different way. So here we go. That's the doc table. So open the data, go to the docs table and follow the instructions from your teacher and your activity guide. See the full level. And that's my problem right now. I can't really sign in because I'm on my personal account, but I can only sign in with my work account. So that's the downside here. But if you're interested, you can just follow the link there. It's a nice way to show what histograms are useful, if bar graphs are better, bucket size and all of this. And it is in App Lab, which might be a little bit more interesting for students to work in the spreadsheet if they've already done this. So if we look into all the integration of computer science, all the possibilities to integrate computer science into our standards. So the easiest way, for example, if you would use open middle problems, those could be an unplugged, you could consider that potentially an unplugged activity, which means it does not require any further computer science, but it's still any further computer science equipment, but it still tackles some of the skills that are needed in there. So all the other algorithmic steps, decomposition, pattern recognition, which is a lot of what's going on in algebra. That's a simple integration, but again, we have to start somewhere, right? If we go for the other step that I showed with CS and math and Scratch or on code.org, that would be a little bit up because we're actually using technology or integrating that one step further into our curriculum. Writing programs, again, that was the model for the modeling, predicting, almost there. This last step of a very complex integration is going to be a very hard reach to get through, I think. But again, we have to start somewhere. A simple integration might be everything that we do at this point. So if you want to use those unplugged or those everyone can do activities, rethink your practice. So instead of a worksheet, maybe ask ChatGPT to use or to create debugging approaches problems. So that could be an error analysis that can be 2 truths and 1 lie. Especially for those very dry skills. So you give them 3 answer opportunities. 2 of them are correctly solved, and the third one is not. I like to do that, especially with properties of powers, which is traditionally more of a dry subject. So that would be a nice thing to do instead of just a regular worksheet. A scavenger hunt, so that essentially means chop up a worksheet, write the question to problem number 1 on the top of or next to the question for question number 7, give them the answer, distribute the problems all around the room, and then let students find their way through this scavenger hunt. So if they complete the circle of, I don't know, 10 problems or something like that, they know they did it right because it's self-checking, self-correcting, because you make a loop out of the questions, although not in order 1, 2, 3, 4, 5, 6, 7, 8, 10, but 1, 5, 2, 9, 9, 8, something like that, more randomized. And they can automatically, if they don't get through the loop, they have to go back and figure out what went wrong. And that's another way to have them practice, but it gets them out of the seats. The students are usually a little bit more excited about those things. Collaboration also as part of the simple integration of computational thinking, just making sure, oh yeah, we've got this. We're in this together, something like that. We can figure it out. And tinkering approach, I think most prominent in the open middle problems. There's a whole website, openmiddle.com, which is sorted by grade level and skill strands. So there's almost something there for everyone. And instead of telling students on how to solve something, have students write their own how-to summary, like how would a computer solve this? How would I solve this? Especially in the Algebra 2 heavy parts of or simplifying rational expressions, something like that. Oof, yeah, it's a little. And maybe why not be intentional about using this computer science vocabulary in your class? So instead of error analysis, call it debugging. So I'll just say I just want you to tinker with this, play around with it. Just a little bit of this. Again, my personal summary of this one what I found is that computational is more, not necessarily better, but it's just more than just computing. It's a part of computing, but it's more than that, and that's a good thing. So thanks for coming virtually, And I think there's still like 3 minutes left to ask some questions if you have anything. If you want the notes, I think Liz is going to send them out, or you can email me directly, because all the links in there are clickable and should work. So thanks for coming. I guess that's what it is at this point.